In October of 2016, DYN DNS, one of the largest DNS providers in the United States, was attacked in what is now known as the largest DDoS or distributed denial of service attack in history. This was a massive attack that turned ordinary devices into weapons. These are IP cameras and printers that are in everyone's homes. And it really is the vanguard for a new era of internet attacks powered by these everyday devices. So if we consider the modern city, it's already full of low power, low cost, internet connected devices. We call these IoT, or Internet of Things. This includes things like IoT power grid monitoring, IoT smart lighting controls, IoT video surveillance for security or even baby monitors, and IoT shipping containers, such as the ones that allow shippers to track the GPS location of their goods as they're taken to their destination. However, there's a major problem in this city, and that is that many of these devices often have major security flaws. Now, if we consider the typical IoT device, we can evaluate it upon three different categories. That is, whether it's low power, low cost, or secure. Advances in technology has allowed the proliferation of low power and low cost devices. However, the focus on these two categories has really led to the security being ignored. Now, in order to understand this more, we spoke to a number of experts in the industry, and they all kind of said the same thing. And that is, when you're making 100 million of something, every penny counts. Every penny costs $1 million, and every penny counts in high volume. So that makes us understand that these IoT devices are hard to produce in large quantities and also be cheap, but we believe that all IoT devices can be secure. They can be low power, low cost, and have security guarantees. So how do we solve this problem? And we kind of asked ourselves this question and looked to the world to see how other people have done it. And Android is a very good example of this. Back in 2007, the only smartphones on the market were things like BlackBerry and Apple iPhone, and these things were proprietary and expensive because they had custom hardware and custom software. However, the Android operating system was released by Google, completely open source and free to use by anyone. And nowadays, it has over 1.6 billion devices using Android, over 400 manufacturers, and it was all enabled by its open source license. So, in order to solve this problem, we will be releasing the EPIC project. The EPIC project is an open source IoT cryptographic solution that incorporates modern, cryptographically secure algorithm running on an optimized physical hardware design. We used a number of resources for this project, including a Lattice Icestorm FPGA, modern elliptic curve cryptography algorithms, and an open source toolchain. To speak a bit about the hardware involved in this project, I'd like to now introduce Asif Versi.
Thanks, Derek. So when we started to look at this problem about a year ago, we realized that we needed to implement our design at the gate level. Not that gate level, but the digital gate level. These digital gates are the atomic elements of any digital circuit. These gates can also be looked at like building blocks, Lego blocks. We have about 8,000 of these to play with, and we can create any digital design we want. We chose to use an FPGA because it allows us to change these Lego blocks however we want, whenever we want, allowing for rapid iteration and design. Now I'd like to pass off to Satya to talk about the software solution.
To implement the software side of our project, we wanted to implement a public key cryptography algorithm on our FPGA. For a brief primer on what public key crypto is, let me give you a brief primer for what public key crypto is. In public key crypto, every user has a public and private key. The public key is shared with the world, and the private key is kept secret so only you know what it is. When Bob wants to send a message to Alice, say, "Hello Alice," he's going to encrypt the message using Alice's public key, which is going to return a ciphertext which is clearly illegible. Bob can safely send the ciphertext over any public channel with the knowledge that no random person will be able to read it. When Alice receives this ciphertext, she's going to decrypt it using her private key, which is going to return the original message of "Hello Alice." Now, there are many algorithms that implement both the encrypt and decrypt black boxes, and the first we chose to evaluate was RSA. RSA is one of the oldest and most commonly used public key crypto systems, and its math is relatively simple. So what we did was we went ahead and built the data path that we put on our FPGA that implemented the RSA protocol. However, the current standard requires key lengths of at least 2048 bits, and with our processor design and that key length requirement, we achieved a data path that took 43,122 LUTs. If you recall, this is almost 6 times as large as our requirements. So we switched to elliptic curve. Elliptic curve is a newer public key crypto system, and the math behind it is much more complicated than the math behind RSA. However, this additional complexity allows us to have much smaller key sizes. An elliptic curve key length of 256 bits has the same security guarantees as an RSA key of 3072 bits. And with that in mind, we were able to design a core data path that used up 6,322 LUTs, which is well within our requirements. Now with that brief overview of public key crypto, I'm going to bring back Asif to talk about the tool chain, which kind of brings together the hardware and software portions of our project.
Thanks, Atya. So when we started out, we started by creating our EPIC hardware design and our EPIC algorithm. This was our elliptic curve implementation. We took our hardware design and verified it using iVerilog, which is an open source tool, and programmed our FPGA using the Project iStorm, which is another open source tool. This gave us our EPIC cryptographic coprocessor. Now we needed to put software on it. We used our own LC5 programming language and a custom compiler, which we ran through a verifier in Python, which was then used to program our EPIC cryptographic coprocessor, which gave us our final result of our EPIC chip. Now I'd like to pass it off to Neil to talk about the demo.
Thanks, Asif. So let's start by going through an overview of how EPIC should work in action. So because EPIC is so easy to actually integrate directly into your IoT device, you can essentially use this and plug and play directly with whatever IoT switch and controller and receiver you'd like. For example, with an IoT smart door lock. So if you don't have the EPIC modules included in your design, you could essentially have an insecure communication channel between these two. Because as Derek mentioned earlier, there could be major security vulnerabilities with the communication between the two. However, once you activate these EPIC modules, you can use them to request a signature that can be sent over the existing communication channel, and the signature can be sent over on the other side to the EPIC module and then verified, which makes the entire communication channel secure, which makes your entire house secure. So I hope you guys are really excited to see EPIC in action.
As Neil just showed you, this is EPIC, and this is how it solves security for IoT devices. EPIC makes IoT devices secure, which means that EPIC makes cities secure. And this is really exciting, because this city that we spoke about earlier can no longer experience the sort of attacks that we mentioned when using the EPIC module. This makes us very excited, and we hope it does for you too. Thank you.